Welcome. Today we'll discover the binary number system, the secret language that powers every computer, phone, and digital device around you. See these zeros and ones. They might look simple, but this pattern, 1,011,010, actually represents the number 90 in decimal. Amazing, isn't it? Before diving into binary, let's understand what a number system actually is. A number system is simply a way to represent numbers using a set of symbols or digits. Think of it as a language for counting. There are several number systems used in computing and mathematics. We have decimal, which uses 10 digits from 0 to 9, and it's what we use daily. Binary uses just 2 digits. 0 and 1 octal uses 8 digits, and hexadecimal uses 16, including letters A through F. Today, we will master the binary system, the foundation of all digital computing. Let's quickly review the decimal system you already know. We use 10 digits, 0 through 9. That's why it's called base 10. The magic of number systems lies in place values. Each position has a different value based on powers of 10. Take a number 5847. The 5 is in the thousands place, worth 1,000. The 8 is in the hundreds place, worth 100. The 4 is in the tens place, worth 10. And the 7 is in the ones place, worth just 1. To find the total value, we multiply each digit by its place value and add them up. 5 times 1,000 is 5,000, plus 8 times 100 is 800, plus 4 times 10 is 40, plus 7 times 1 is 7. That gives us 5847. Remember this concept, because binary works the same way, just with powers of 2. Now here's the exciting part. Binary is the simplest number system possible. It uses only 2 digits, 0 and 1. That's it. Just 2 symbols to represent any number. 0 represents off, false, or no. 1 represents on, true, or yes. Think of a light switch, it's either on or off, nothing in between. The word binary comes from bi, meaning 2. And here's a fun fact. Each 0 or 1 is called a bit, short for binary digit. Bits are the building blocks of all digital information. But wait, why do computers use binary? Why not use our familiar decimal system with 10 digits? Great question. First, computers use billions of tiny switches called transistors. Each transistor can only be on or off, perfect for binary. Second, having just 2 states makes the system extremely reliable. Third, binary operations are lightning fast for electronic circuits. And fourth, with only 2 clear states, there's less chance of errors. Imagine a light switch in your room. It can only be on or off. Billions of these tiny switches working together is how your computer thinks. Let's learn about bits and bytes. A bit is the smallest unit of data in a computer. It's a single 0 or 1. That's all a computer can understand at the most basic level. Now, when we group 8 bits together, we get a byte. Look at these 8 bits arranged together. 1 byte can represent 256 different values, from 0 to 255. That's enough to store a single letter, number, or symbol. Bytes combine to form larger units. 1,024 bytes make a kilobyte, 1,024 kilobytes make a megabyte, and it goes on to gigabytes and terabytes. Your phone might have 128 gigabytes. That's over 128 billion bytes. Now here's the key insight. Just like decimal uses powers of 10, binary uses powers of 2. This is the secret to understanding binary numbers. Starting from the right, the first position is worth 1, which is 2 to the power 0. The second position is 2, then 4, then 8, 16, 32, 64, and 128. Each position doubles the previous one. This doubling pattern is beautiful. 1, 2, 4, 8, 16, and so on. The formula is simple. The place value equals 2 raised to the power of position minus 1. Now let's see place values in action. We'll convert the binary number 10, 11 to decimal step by step. Look at our binary number, 10, 11. Each digit is in its place value position. The first digit is 1 times 8, the second is 0 times 4, the third is 1 times 2, and the last is 1 times 1. Now we multiply each digit by its place value. 1 times 8 is 8, 0 times 4 is 0, 1 times 2 is 2, and 1 times 1 is 1. Finally, we add them all together. 8 plus 0 plus 2 plus 1 equals 11. So the binary number 10, 11 equals decimal 11. Perfect! You just converted a binary number to decimal using place values. This is the foundation of understanding how computers represent all numbers. Now here's the key concept that makes verification work. Each bit position doesn't just have a number, it has a power of 2. Look at this carefully. The rightmost position is position 0, and 2 to the power 0 equals 1. Position 1 is 2 to the power 1, which equals 2. Position 2 is 2 to the power 2, which equals 4. And position 3 is 2 to the power 3, which equals 8. This is why when we see a 1 in position 3, we multiply it by 8. The formula is simple. The value at any position equals 2 raised to that position number. This is the secret to understanding binary verification. Now let's learn the positional multiplication method. This is the systematic way to convert any binary number to decimal. Here are the 5 steps. First, write down your binary number. Second, assign place values from right to left using powers of 2. Third, multiply each digit by its place value. Fourth, add all the products together. And fifth, that sum is your decimal equivalent. The beautiful part is this method works for any binary number, whether it's 4 bits, 8 bits, or even 32 bits. Let's count from 0 to 15 in binary. Watch the pattern carefully. 0 is 0, 1 is 1, 2 is 10. Notice the rightmost bit flips. 3 is 11, 4 is 100, and so on up to 15, which is 1111. Here's a powerful insight. 4 bits can represent 16 different values from 0 to 15. That's 2 to the power of 4 equals 16. More bits mean more possible numbers. Let me show you a real-world analogy that makes binary super easy to understand. Think of binary as a series of light switches. Each switch can be either on or off, right? Well, on is like 1 in binary and off is like 0. It's that simple. Here's our example with 4 switches. Look at them. The first switch is on, which is 1. The second switch is off, which is 0. The third switch is on, which is 1. And the fourth switch is on, which is also 1. So we have the binary number 10, 11. Each switch also has a place value, 8, 4, 2, and 1. Now let's calculate. We take the place values where the switches are on. That's 8 plus 0 plus 2 plus 1. Adding them up, 8 plus 2 plus 1 equals 11. So binary 10, 11 represents decimal 11. Simple. This is exactly how computers work. Deep inside your phone or laptop, there are billions of tiny switches. When they're on, it's a 1. When they're off, it's a 0. And by combining millions of these switches, computers can store all your photos, videos, messages, and everything else. You might wonder, where do we actually use binary in real life? The answer is multiple domains. Digital images store each pixel's color as bits. Text messages encode each letter as 8 bits. Music files convert sound waves to binary. And video games store all graphics and logic as binary data. Here's a fun fact. The letter A is stored as 1,000,001 in binary. That's 8 bits, or exactly 1 byte. Every letter you type has its own binary code. Now let's see how computers actually store binary data. Computers don't store it as digits on a screen. Instead, they use tiny physical cells in memory. This is RAM, random access memory. It's where your computer temporarily stores all the data it's working with. Here's a visualization of memory cells. Each cell is a tiny switch that can hold either a 0 or a 1. See how they light up with different colors: green for 1, orange for 0. When we group 8 of these cells together, we get 1 byte. This is the standard unit computers use to measure storage. So here's what you need to remember. Each cell stores 1 bit. A byte is 8 bits, and your phone, computer, or tablet has billions of these cells working together. Let's wrap up everything we've learned about the binary number system. Here are the 6 key concepts. First, binary uses only zeros and ones in base 2. Second, place values follow powers of 2, doubling each time. Third, 8 bits combine to make 1 byte. Fourth, to convert decimal to binary, divide by 2 and read remainders upward. Fifth, for binary to decimal, multiply each bit by its place value and add them together. Sixth, and most importantly, computers use binary because transistors work like simple on-off switches. Notice how each concept builds on the previous one. Remember, binary is the absolute foundation of all digital technology. Every single app, every game, every video, every photo you've ever seen is made of billions of zeros and ones. You now understand the secret language that powers the entire digital world. Keep practicing, keep exploring, and keep thinking like a computer scientist.